So, starting in chapter 13, if you look on the first page, it gives you a little bit of the history of this astronomy kind of stuff, gravity. In a lot of the other chapters, they don't start with a history of anything. Like, a lot of research or history behind energy and work comes from James Joule and something Carnot. I don't remember. There's all. I'm sure there are plenty of historical figures that follow all that other stuff too. But I think astronomy has a special place in science because it really is the origins of scientific thinking, right? If you go back to, again, like the 1570s, the 1600s, and you look at the kind of medicine that was around, they didn't study medicine in a very scientific, objective way. A lot of it was based on philosophy, really, at that time. Just before it, if you look at the kind of philosophical thinking, it was based on the idea that any truth of the universe, if you think about it long enough, you can figure it out. Right? That was kind of, is it Plato? I don't remember. One of those guys from Greece. It's like, that's the philosophy, right? If you can think about it hard enough, any human reasoning can eventually figure out all the truths of the universe. And so it would be like, whoa, if you're sick, then there's bad stuff in you. Let's bleed it out. And like, if there's something wrong with your head, we'll just drill into your head and do a lobotomy. Like, that was the kind of medicine that was going on. It's crazy. And astronomy was kind of like that too. We had the belief that the sun was at the center, the Earth was at the center of the universe, and the model was from a guy named Ptolemy. It's kind of weird how it's spelled. Ptolm. E-M. Ptolemy. E-M-Y, yeah. It starts with a PT, which is always weird. In any case, it's Earth-centric. And the way the model was is that here's the Earth and the sky, and then it's like surrounded by this sheet that had stars like attached to the sheet. And that was the edge of the universe, was not very far away, and these stars, these little specks of light, were just on the sheet, and the sheet would rotate around the Earth. And that if you poked through the sheet, you would see the heavens and the gods, right? But that's the thing, is they didn't have telescopes. There's no way to see more than just Venus and Mars and Jupiter. Those were really the only planets that you could really see from the naked eye. And so that was the model. And it was very indicative of the kind of philosophy that people had of what humanity was, that humanity was special and everything, humans were the center of everything. God created humans specifically because we're special. And it wasn't until Tycho Brahe and Johannes Kepler and Galileo Galilei to systematically look at the data and make observations and find that that model just didn't fit. Well, not only that, but there were some other things that were super weird about the model, like when they were trying to figure out how, what were they called? I'll worry about that another time. But the old model just did not mathematically work out. It didn't make any good predictions, and they couldn't make the numbers fit. And so, but it was based on those observations that eventually you have Copernicus put out this idea that, okay, maybe the sun is at the center of the universe. And eventually, there are more observations. I can't remember if it's from Tycho or from Galileo, but they see that there are other galaxies that were kind of had their own stars and their own, I don't think they could see that they're their own planets, but they could see that there were stars revolving other stars. And they then figured that, okay, then the sun can't be the center of the universe either. That our solar system is not special, that we're just one solar system and one galaxy in the midst of other galaxies and so on and so forth. And I think that's just philosophically important because it kind of made humans not special. It made it so that we could look at natural phenomenon more objectively and not just that everything has to do with humans and our special spirit and our soul and whatever. And I'm not saying that like all that stuff is wrong. I think it just introduced this idea of being more data-driven and objective, right? Looking for evidence. And so that's where it starts. That's where science starts. And then from there, it just spreads to other fields. Being systematic with measurements. The other thing, too, with the astronomy, the history of the astronomy that I think is special is it was because their need to solve this problem with making the data fit the model that they approached Isaac Newton, and Isaac Newton took this problem and had an imperative to solve it, and then was like, well, let me invent calculus, and then I'll use that and solve it, and figure out his laws of motion, and he documented everything into his Principia, and it was kind of under this imperative, I suppose. He was kind of given an opportunity or pushed to do it. So I think that's also important. So you look at the history, there's a lot of connections there for the start of science. And so I think it's important. If you're interested in astronomy, definitely worth reading up on that or learning about that stuff. It's really neat. I think having watched Hidden Figures recently really kind of has rekindled my interest in astronomy and aerospace. It's cool stuff.
Are we gonna have a history test on the test?
No. None of this is on the AP exam at all. But physics. That's the thing. It's like particularly for this topic, it is particularly interesting because some of the other fields or other topics, the history behind it is kind of whatever. Not as revolutionary as this was. Okay. So let's talk about gravity and orbits and all that stuff. So when you talk about orbits, they follow Kepler's 3 laws. And it's in the book, so you don't have to copy it down. I wrote it down in my notes just so I can show you guys. First, planets move in elliptical orbits. They move in ellipses. That was one of the big discoveries that Isaac Newton made through his calculus and through his math. He discovered really 2 things. He kind of, I should say that Kepler first figured that it should be an ellipse, but he couldn't mathematically prove it. So Kepler made the observation, and he may have posited the idea, but it was really Newton who came up with the inverse square law and then mathematically demonstrated that because it's an inverse square law, objects must move in an ellipse. Okay. So I would say that Newton gave the mathematically rigorous explanation for elliptical orbits, but maybe Kepler was the first one to say it looked that way. In the book, it says that planets move in elliptical orbits with the sun at one focus. Technically, that's not true. The sun doesn't have to be at the focus. It's really actually the center of mass that is the focus. So when you look at an ellipse, it's like a circle where you take the center and then you stretch it, right? So you have 2 centers, so to speak, 2 foci. And the rule of an ellipse is that when you draw an ellipse, like a circle with a radius, and that every point on the circle is equidistant from the center, An ellipse is such that every point has a distance where the sum of the two distances from the two centers is constant. So there's a classic example of like you take two pins, you put it on a cork board or something like that, and you make a string, you make a circular string, and then you make it taut so it makes this triangle, and you draw that around, that will draw an ellipse. Okay, so that at any point, if you're looking at this length, or if you go over here and this one, the sum of those two lengths are always the same. That's what makes an ellipse. Mathematically, that's how it works out. So it's always drawing out the same, that total length always stays the same. So that focus, the sun in our solar system happens to sit on top of that focus because it's so massive that the center of mass of our solar system is very much concentrated within the sun. But it's not actually in the sun. The sun itself kind of wobbles around this center of mass. If you look at binary stars, they both orbit because they're both of similar mass. Maybe one's much bigger than the other, but the idea is they're massive enough to cause the other to orbit, and they both orbit around generally a common focus. So they'll both spin around it. But in the case of our galaxy, our solar system, the sun is pretty much right on top of it. Jupiter is really the only planet that's massive enough to cause the sun to wiggle. Every other planet is pretty much insignificant. Okay, so planets move in elliptical orbits with the sun at one focus. The bigger idea is that planets orbit around a focus. That's probably or objects in space orbit around a focus. Okay, so that's the first law. So when you look at an ellipse or an orbit, there are a couple words or terms that come up if you're interested in astronomy. Okay, now this is something that you need to know for AP exam. This stuff at the top, not so much, but I want to share with you anyway. There are some specific astronomy terms for two specific points on an orbit. Is the point of closest approach and the point of furthest approach, or whatever, the furthest distance and closest distance. At those points, it is the only 2 points where your velocity will be perpendicular to your radius. Right? Every other point, when you're moving, may have some odd angle because it's not a perfect circle, right? Your velocity that's tangent is not necessarily perpendicular to this radius vector, your position vector. But at those two moments, it is. And actually a lot of the math behind describing or choosing a unique ellipse or describing that unique ellipse is based on those 2 points. Because they are at special positions. The way your ellipse is facing is kind of based on those 2 points. So the close one, if you're talking about the sun, and this is from the history of the development of this language, is your perihelion. So your perihelion is the close to the sun. Peri for close, heli for sun, after Helios, the sun god or whatever. Whereas if it is the Earth, then it's the perigee, right? G root for the Earth, right? And then if you're just talking about any general orbit around some other planetary body, you would talk about the periapsis. As opposed to the furthest distance, you have the apohelion or the apogee or just the apsis. Okay? Now those terms you don't have to memorize, but who knows? Maybe you can score extra points if you stick them in there if it comes up. Or it's just good to know if you ever pursue astronomy. Okay. There's a couple significant. It's actually can get significantly more complicated than this. The math of ellipses are really insane because this is all in 2 dimensions. So imagine for a minute that not only do you have this, okay, you have to account for, okay, what direction can the ellipse face? How stretched out it is, your semi-major axis length. Imagine if you could tilt it. Now you have that angle. You can tilt it like this. You have that angle. And so you have actually many degrees of freedom in how you shape an orbit, right? And the transformations and all that stuff for it is pretty nuts. So we don't do any of that in this class. What we'll find is that everything that the AP exam deals with at this level is just circular orbits that are two-dimensional. It's just flat. You just pretend it's flat and it's a circle. And so we will interpret a lot of these problems specifically for circular orbits. Circular orbits are nice. They're simple, they're neat. And they're pretty prevalent, to be honest. So, okay, Kepler's second law. A line drawn between the sun and a planet sweeps out equal areas in equal time. What that means is that as an object tends to get closer to the focus, because it is closer, the area that it sweeps out is less per angle change. So it needs to sweep out more angle, right, to cover the same amount of area in the same amount of time. This is based on essentially conservation of angular momentum. As your radius goes down, your momentum has to go up to conserve angular momentum. Or more practically speaking, generally, as you get closer to the sun, you go faster, and if you go further away from the sun, you go slower. So when you look at comets, asteroids, whatever, or things, or if you watch like, what was it called? That movie with Bruce Willis and Armageddon. Armageddon. Remember Armageddon? They fly and get really close to the moon, and then they do a boost to do an acceleration, right? Gravity boost or whatever. So they get close, they go faster, and then they accelerate so that they can slingshot around and go really fast from the backside to land on an asteroid, to land on an asteroid.
So that's physically possible.
Yeah, we do slingshots all the time. We try. Sometimes we can plan trajectories where we will get close to one planet, so that as we get close, we speed up and we do a boost so that we can slingshot ourselves to another one. Let's see. Okay, so you get close, you go fast. You're far away, you go slow. The third law, actually, I'd rather use this one because it's a little bigger. In the book, it says the square of a planet's orbital period is proportional to the cube of the semi-major axis length. I think that's a mouthful. Mathematically, that's what it says. T squared is proportional to a cubed. I think that's a lot easier to remember. T squared, the period squared, is proportional to the semi-major axis length cubed. It's kind of a weird relationship, but we can show that mathematically in a minute here.
Is that not alpha?
That is just A, which is your semi-major axis length. So when you look at ellipses, generally the nomenclature is your semi-major axis length is lowercase a, and your semi-minor axis length is lowercase b. So that, I'm not sure if I'm remembering this correctly, but it's like 1 over a squared plus 1 over b squared equals to 1 over something else squared. That's the equation of an ellipse, right? Something like that? All right. Vaguely remember that. Okay, so in the case of a circle, as an ellipse, so a circle is really just a special case of an ellipse. When the two foci are on top of each other, then you create a circle. Then your a cubed just becomes r cubed. Okay. All right. So looking at the three laws, we'll look at them closer in a minute, but these laws, quote unquote, there are mathematical representations of them, but the way Kepler presented them, they were really more observations at the time than laws. And then Newton came along and figured out all the math. So there's those three laws, and then there is Newton's law of gravitation, or of gravity. And it describes in here in the book, it only gives you the magnitude of the force. Okay, it doesn't really tell you anything about direction. Simply the direction is just they attract each other, right? But there's actually a good bit of nuance to this equation. In the equation sheet on the AP exam, it writes it slightly differently. And on the equation sheet, it's like this. It is a negative, and then there's this r with the arrow on top of it, the unit vector. Okay, it's the unit vector r. The thing is, gravity is a force, and forces are vectors. So mathematically, this is a more complete representation of force of gravity than this one. This is only the magnitude. This is more generalizable. So in other words, if I, in the diagrams that they have in the textbook, again, everything is flat. It's 2D. So I can say, well, this is pointing that way and that's pointing this way. But if I want to create a model for, let's say, the orbit of the moon, right? And the Earth is this tilted axis, and the moon kind of does this thing, and everything is in 3 dimensions, and it's all tilted. So at any time, if I want to try and mathematically describe the location of something, I have I, J, and K. I have to worry about all 3 directions. And so if I want to represent the force of gravity from that, and I want to program it, or I want to try and model that and make predictions with it, I can't just know the magnitude. I need to know the direction, so I know where it goes next. So you have the unit vector. If you remember what unit vectors are like, here's an example. If I want to point at something that is 45 degrees from me, the unit vector is there so that the whole point of a unit vector is only to give direction, so that its magnitude is 1. The length of a unit vector is always 1. So that if you do Pythagorean theorem on this, the length of this is 1, but it tells you how far over and how far up, so that you know which direction to point, and then how long it is the coefficient. Right? Here's the magnitude, here's the direction. Okay, so what this does, the difference between this one and this one is, by having the negative r hat, it tells you that here's, let's say, this is object 1, here's object 2, and I'm looking from the perspective of object 1. Object 2 is a distance r this way. Then the force is that way. If I'm object 2, then the distance of our object 1 is this way, and so the force is that way. Basically, it's a mathematical way of showing that it's a force of attraction, and only attraction. You will never push an object away with gravity. You'll only ever pull something in with gravity. Our universe would be very interesting if gravity could push as well as pull. Okay, so that's all this is really trying to say. It's an attractive force. And then, okay, so now let's look at the numbers, or the equation a little closer. It's Gm1, m2. Notice that it has the mass of both, because gravity is a mutually attractive force. Remember how we said when we were studying Newton's third law that if gravity pulls on me with 150 pounds of force, I must also pull on the Earth with 150 pounds of force up. Pulls both ways. Reza, what's up?
So the part that you said, when if you have a boost, you have a boost like to the gravity of something and it pushes you back. So is that friction too?
Pushes you back.
You said like if it's like a rock that's going to gravity of another planet, for example, it pushes you back.
I didn't say it pushes you back. A lot of times what we do is when we go around a planet, we speed up because we get close. And at that moment, it becomes very efficient to do our boosters, to engage our boosters to do what we call a delta V, which is a kinetic energy change to speed up. And it doesn't slow us down. What it does is we use it to turn quickly and speed up. Yeah. It's really just to turn. In other words, if I'm going this way, and I want to go that way, I don't want to have to just fire and accelerate this way. It's very convenient that if there happens to be a planet in the way, I use the planet to turn myself, to change my direction, right? So that's what that was about. There's not much about friction in any of this. Friction is, when surfaces come close together. Hopefully there are no planets that are undergoing friction with other planets. Be pretty catastrophic. Okay. So, right. So I was saying, really, because of the third law, right? Forces always act in pairs. You'll see that gravity always acts in pairs. It's always a mutually attractive force. It never happens where you have a planet pull on something, and only it pulls on something. If it is pulling on something, it is being pulled towards it too. They're always pulling on each other. So, and that should make sense. It should be symmetric. It'd be weird if if a planet could pull on another planet more than it was pulling the other direction. It always pulls equal force. So that's why it's M1 and M2. Second is inverse square law. Okay, so if you look at this graph, the further you go away, your force gets weaker by the square of the change. So if I get twice as far away, then I get 1/4 of the force. Or if I go 3 times as far away, I get 1/9 the force. It drops quickly. Okay. The last thing to look at is this constant, this big G, this gravitational constant G. You do not have to memorize it. It's on the equation sheet that you get on the AP exam. But like certain constants, it can come up a lot, and it can be convenient to know it well, like Avogadro's number. Right? If you're doing chem and you want to know Avogadro's number. Not only that, but there are other constants that sometimes are convenient, like knowing the density of water or knowing temperature at sea level. Little things just kind of you use often. So that's kind of one of those. It's good to know. So regarding the units, sometimes I forget what the units of G are because there's a lot of stuff going on there. What you can do is just do dimensional analysis on this equation. So on the left-hand side, it's a force. It has to be in newtons. On the right-hand side, there's 2 masses on the top and 2 meters on the bottom. Your G needs to cancel out the meters, right? So you'll see how G has kilograms on the denominator squared. And it has meters squared on the top, so that it cancels out with those meters and those the kilograms and the meters that comes from the other parts, so that you're only left with newtons. If you're not kind of following me on that, imagine plugging this in to there and plugging in all those other numbers. You'll see that these meters squared cancel with those meters squared, and these kilograms squared cancel with those kilograms squared, so you only end up with newtons. I had a student ask me last period, what is the meaning of G? First, notice that it's a really small number. It's tiny. It's really small, right? So, and this is for kilograms, right? So, if you have something that is even really close, like a millimeter, right? A millimeter would be like a meter times 10 to the negative 3, and you square it. Okay, so that's times 10 to the negative 6. That's still times the G puts you at times 10 to the negative 5. You're still at a really small force. If you have something really, really close, a millimeter away, you're still talking about micronewtons, really small amount of gravity. If somehow you could get a kilogram of material a millimeter away from each other, right? And when you look at space, we're talking about millions of meters on the denominator. So compound that with this, you're talking about really, really small forces. Okay, really small forces. Or you have to have extremely massive objects. So a few pages later, it gives you an astronomical data table. look at these masses. Okay, the mass of the Earth, 6 times 10 to the 24. You do, so think about that for a second. A mass of 6 times 10 to the 24, that's, if a million is times 10 to the 6, that means that it's 6 million, right? To get your 24 zeros. All of that so that you experience a weight of like 150 pounds, right? All that mass below you, pulling on you, pulls you with like, whatever, 130 pounds, 150 pounds. So the important thing to know about gravity is it's really weak. It's really weak. But it only ever pulls. It never pushes. So you give a universe 6 billion years or 4 billion years. Over those billions of years, particles will pull and pull and pull, and then they'll come together. So, and then you'll create planets. So it takes a long, long time, but it pulls, and eventually it'll happen. A couple other comments about G. When you're looking at G and you're wondering, okay, how do we figure out G? There are some things, a lot of things in science and engineering where we look for patterns, right? So some of the experiments that we've done, the labs that we've done in this class, we look for relationships. We change one thing, we look at how the other thing changes. Is it change linearly? Does it change inversely? Does it change quadratically? Whatever. We look for these patterns, but that only gives us a portion, the relationship, right? So we can say it's linear with it. If I double this, that doubles. Or if it's inverse, I double this, the effect doesn't happen. We know how it changes, but a proportion doesn't help us determine the actual value, right? Not the actual values. So what ends up happening is we study the science, we study the changes, we figure out how things change and relate to each other. We propose an equation that is often initially a proportion of some sort. Like, I think that heat transfer is related to the 4th power of temperature difference, which is one of the rules out there. But you need a constant to make it equal. Okay? You need a way to figure out the actual value of it. And a lot of times it's experimentally determined. So this is, I believe, an experimentally determined and agreed upon by the scientific community value for the relationship between masses, distances, and then the force. It's a constant that is experimentally determined. Some constants can be theoretically determined. So we'll see later when we study magnetism how moving charges attract each other. There's a constant there. That constant is 4 pi times 10 to the negative 7. It's a very specific constant for it to be 4 pi. Because pi is an irrational number. It goes on for infinity, right? How are you supposed to choose that, measure that? You can't measure that, right? That's a theoretical outcome. But sometimes it's measured. For example, how we consider the length of a second is agreed upon by the scientific community by the half-life of cesium or something like that. They have this block of cesium in France, and they determine how heavy it is, and they figure out how much time has passed by for it to get cut in half, and they count like, okay, well then we'll say this much time is 1 second. So some things, a lot of things are just agreed upon. They're not theoretical, they're just experimentally determined. So this is one of those things you can experimentally determine. Okay. Any questions so far? The laws, pretty conceptual, I think. The equation's not super crazy. There honestly isn't too much nuance. It's not like elastic versus inelastic equations. There's not too much because we're only dealing with circular orbits. So I think it'll be pretty straightforward. Okay. So, speaking of big G, how does that relate to little g? So little g we use on the surface of the Earth. We usually say it's 9.8, like 9.8 meters per square second. That really just comes from the first half of, or the front part of Newton's law of gravitation. Effectively, everything that doesn't include your mass, right? If we take the mass of the Earth and we multiply by g, and we divide by the radius of the Earth, for the most part, everything on the surface of the Earth, this is constant, right? The only variable is really your mass, right? So little g is pretty much a constant. And so you can calculate that. In the book, they have a table about different values of little g, right? So like if you're on Mount Whitney, you lose like 0.01 meters per square second, or if you're in a space shuttle, you know, you lose maybe 1 or 0.9 meters per square second. Be careful when you look at this and you look at the height. Notice that this is the height, not the distance from the center of the Earth. When you use this, r is not the height, it is the distance from the center of that object. So the radius of the Earth is like 6,370,000 meters. So 300,000 meters is really small relative to 6,370,000 meters. That's why your gravity doesn't change that much. Okay? It may look like you've changed your distance by 30 times. It's not. You got to keep into account the radius of the Earth. Which actually brings me to another point. I know this is a lot of different things I'm saying. A lot of this, you have to be patient with me because some of this stuff that I'm telling you is not on the AP exam, but I'm an aerospace engineer. I think this is really important information, so I'm going to tell you anyway. This equation, Newton's law of gravitation, is for two particles of certain masses attracted to each other. There's nothing in here that says anything about the volume of those particles. It is kind of assumed that they are point masses. It's a very theoretical outcome. Most objects are not point masses, right? They have volume, they take up space. They are a collection of particles, which means that every particle in your body is attracted to every other particle and is pulling on every other particle. So how do we deal with rigid bodies? If you go through the math, and actually I think Hyperphysics does it. There's a website called Hyperphysics. It goes through the derivation that for uniform spheres, it works out that if you have one uniform sphere and you have another uniform sphere and you add up using calculus and you integrate all the forces from every differential mass, a little piece of mass in each sphere attracted to every other piece, it works out that is effectively as if you took all the mass and concentrated it at the center. But that only works for uniform solid spheres. Okay, if the mass is uniformly distributed. So as an approximation, most planets will say are like that, most bodies are like that, but let's say you have a pretty big asteroid that has a weird shape, you can't do that. It is significant enough that if you try and send the satellite towards it, you will mischaracterize the motion of your satellite if you assume all the mass is at its center. Yeah.
Is it kind of like the moment of inertial?
Yeah, it really is. It's like that because this is r squared. See, when you look for the center of mass of an object, that's linear. It's just the weighted average, right? You have x times m. X times m, x times m for each, piece of mass, and then you linearly determine, okay, where's the center? But the force of gravity is not linear. It's inverse square, which means that anything that's slightly closer doesn't experience more gravity, it experiences much more gravity. And so just because your center of mass is just averaging everything, anything that's closer to the front is going to experience, to the square, more gravity and more force. But because the sphere is uniformly distributed, it just happens to work out that this still works if you take all the mass and concentrate it at the center. Okay. So you can do that. You can say for like the Earth or the Moon that the force of gravity is as if you're going from the distance of where you are to the center of the Earth. Okay. Let's see. So going through that, you got little g. Okay. Let's talk about the principle of equivalence. This is actually a pretty deep concept 2. Deep meaning it has a lot of ramifications. So when we look at F equals MA, or whatever, M equals F over A, that was from looking at, like, we took our cart and we pulled on it and we saw how much time it took to speed up. Nowhere in that did it have anything to do with gravity, other than just, we're using gravity to pull on it, right? If we were really good and we were really skilled, we could pull on it with our hands at a constant force, right? If you were really good. And you could accelerate it. But none of that has anything to do with gravity, and yet we say it's force equals mass times acceleration, right? And when I showed you this equation, right, Newton's law of gravitation, without even blinking an eye, you would say that's the same mass. But this mass has to do with the attraction of objects based on some quantity we call mass, and that the more of this stuff there is, the more they pull on each other. There's no reason why the more attracted things are by this force we call gravity should have anything to do with how hard it is to speed it up or slow it down, right? Those are two very different concepts. And yet, experimentally, if you measure, take an object, try and speed it up, and take the object and see how much it weighs, it's the exact same mass. Okay? And why that is the case, well, we didn't actually really figure that out until Einstein. Einstein figured out why motion, what is the relationship between motion and gravity. And if you look into it and you study it, that relationship is this concept of warping space-time. It's kind of a neat idea, but first, let's establish the fact that there's no reason why they should be the same, right? If you try and push and pull on something and it's hard to speed it up or slow it down, we call that inertia. It has an inertial mass. And we take two objects and leave them in space, they eventually pull towards each other, we call that gravity, and it's based on the gravitational mass. And the fact that those two masses are quantifiably the same. Einstein had this really brilliant thought experiment. So imagine this. Imagine you're in an elevator floating in space, and there are no windows. You're just in an elevator, you can't look out. All you can experience is just being in that elevator. If there was gravity, how would you experience gravity? You would feel the elevator push up on you, and you would feel like you're being pushed into the elevator, right? You feel your weight pushed into the elevator. You would not be able to distinguish that from if the elevator had no gravity, but was accelerating upward, pushing itself into you with the exact same amount of force, right? You would not be able to tell the difference. So in one case, we call it gravity pulling you down, and the elevator is pushing back up on you, and you feel that force. And then the other example is a matter of motion, where the elevator is accelerating, and you're experiencing that force. And so he said that then, therefore, gravity and acceleration are one and the same thing. It's not that there's gravity and that there's acceleration. It's that gravity changes the space so that you experience acceleration, which is crazy for anyone to think of. It's a really weird idea, but he did figure that out.
That makes sense. It's not believing it. We're like, oh yeah, of course.
Yeah, no. I think it took a little, it took some papers and took some convincing of the scientific community to get through that. Okay, so that is the idea of equivalence. First, that by themselves, these two equations, there's no reason for the masses to be the same, and that they experimentally always seem to be the same. And then Einstein came along and said, well, they're just two sides of the same coin. It's warped space-time. Okay. Questions so far? Thoughts? Okay. All right. So that is all. 13.1 through 13.4. 13.5. Don't worry about it. See all this integral stuff? We'll do that later. 13.6. This is good. has some important information about specifically circular orbits. So let's look at them for a second. Let's establish the fact that we have a circular orbit. So now what? What can we determine from that? Well, okay. So if you have a circular orbit, how fast do you have to be going to have a circular orbit? You'll notice that when you do a bunch of gravity stuff on the EP exam software, it is very related to circular motion because we look at circular orbits. So all of this centripetal acceleration stuff is going to come up again. The only difference is instead of friction pulling you in and turning the car, or tension pulling you in because you're spinning the rope, it is now gravity that is pulling you in, that is turning you. The force that is now turning you is gravity, which is resulting in your centripetal acceleration. And when you work it out, you'll find that your tangential velocity has to be this value to have circular orbit. That m is the mass of the planet. This m is the mass of the planet. Okay. Once again, this equation is kind of like the collision equations. You don't they're not on the equation sheet, but it can be convenient to have it memorized. Okay, it can be convenient. Okay, so just to give you an idea of how fast that is, if you take the numbers that we had earlier, that I showed you, like the mass of the Earth and the radius of the Earth, if you had an object, like if you could flick a rock that could orbit the surface of the Earth, flick it really hard, it would have to go about 7.9 kilometers per second. Okay, or 7,900 or 7,900 meters per second. That is, well, very fast. Yeah, 25,000 feet per second, something like that. What would that be? Maybe 5 miles per second? I think it's, yeah, it's about 5 miles per second. Okay, that's how fast it'd have to go. If it were to, that's how fast it has to go so that instead of falling and hitting the Earth, it's falling at the same curvature of the Earth, right? To create a circular orbit. If you look at the equation, the further away you are, as r goes up, vt goes down. So actually, the further away you are, the slower you have to go for circular orbit. So the International Space Station is going maybe more like 7,700 meters per second, or 7.7 kilometers per second. But still stupidly fast, right? It's really fast. I don't know if you know about this, like the Cassini satellite that is taking pictures of Saturn. I was looking at this the other day. It is getting towards the end of its life cycle, so they're gonna plunge it into Saturn and take as many pictures as they can before it before it's just gone. It's falling relative to the center of Saturn at like 68,000 meters per second or something like that, because it's so much more massive and the gravity is so much higher. That's just like going really fast. It's really fast. Yeah. Well, that's the thing though. It's so big. So although you're falling faster, you're traveling a bigger distance, and so everything probably still looks, yeah, like you're not falling super fast. Okay. So another thing that comes up, because it's circular orbit, something that comes up a lot on the AP exam is the different ways they ask you questions. So they won't make it easy and say, okay, well, if the radius of Earth is this much, what is the tangential velocity? They'll say something like, what's the period of the orbit? Or what is the frequency if I double the mass of my planet? Or if I take my orbit and I make it 3 times farther away, by what factor does my angular velocity change, or something like that, right? So it's good to remember how your tangential velocity is related to all your angular stuff and your frequency and your period. That will come up. That will come up. Okay. Talking forever. Let's try a practice problem. want you to try number 4. Here. Number 4. Give it a shot. Okay. I'll come around, take a look. Anyone got it yet?
Do we have to like calculate it?
Yeah, you should calculate it. You should actually calculate it. So if you're wondering, it can help to know like some of the astronomical data, like the mass of the Earth times 10 to the 24, and the radius of the Earth. You guys have the internet. It's the same thing. You can look it up. Radius of the Earth, mass of the Earth. These are constants. They'll never. Yeah. No, you can't use 9.8. You know, I guess actually you could. You could use that. But you can't do it for the. Yeah, I guess you could use that. It does work out.
It doesn't matter.
Yeah, that's a very small one.
Yes. You gotta square the radius. Square the radius.
I gotta read stuff. I answered without even reading it.
I was reading this at bedtime.
I know. South Beach.
Okay. Want to see what you got? Be careful. The diameter is 1, but that is not the radius. Times what?
Negative 9? 7? It's 1.6.
Yeah. Times 10 to the negative 4. Alright guys, for the sake of time, there's a couple things left to cover. So, you're looking for something like this. Okay, you're just looking for the ratio of the forces. So if you do your forces, now if you just try to plug in numbers, this is again why I try to advocate, do it symbolically first. Because if you're plugging in 6.67 times 10 to the negative 11, you don't need it. Because you're looking for the ratio, right? So the big G is actually going to cancel. Not only that, the mass, if you're wondering, I don't know what the mass of the dust particle is, you don't need that either, right? Because that's going to get divided out. So in the end, you're really just looking at this, you plug stuff in, you get that. Okay? S.
No, not the left. The second mass, is that the...
This is, oh, so I say M1, M2 loosely, but on the top this would be like the mass of the sphere and the mass of the dust particle, and then this would be the mass of the Earth and the mass of the dust particle. But since they both have a mass of the dust particle, it cancels. Yeah.
Oh.
Okay. We good? Yep. Okay. Almost good. Pretty much from here, you're just substituting. And then I know a lot of you guys sometimes have trouble with the calculator part. Just be mindful about your parentheses, what it is you're squaring, and then you should be fine. Okay. So, last couple things, 15 minutes. Let's look at, now that we've kind of established Newton's laws. Newton's laws kind of reinforce Kepler's laws. Let's look at it mathematically a little bit. And again, we're only looking for circular motion. So Kepler's third law says that the square of the period is equal to the cube of the distance or whatever, right? Let's prove it. Okay, let's prove it. How do we show that? It starts from here. Okay? See if you can follow me on my logic here. If it is going in a circle, it is experiencing only centripetal acceleration. That centripetal acceleration is due to the force of gravity. Because of that, we can determine what the tangential velocity has to be for it to go in a circle. If I know what the tangential velocity is, I can figure out what the angular velocity is if I know the radius, which means that if the tangential velocity is related to the radius, my angular velocity is related to radius. But my angular velocity is related to the period, because it's how often I go around, this 2 pi. So if I substitute that in, now I have a relationship between the period and the radius. And if I solve for t, I'm going to square both sides. I can now demonstrate that the square of the period is proportional to the cube of the radius. Right? These are, we would assume, constants, g and m, for a particular circular orbit. So for any given circular orbit, this equation will tell you if you know the radius, you can get the period. Or if you know the period, you can get the radius. Again, this is another one of those equations that it can be nice to know, because a lot of times on the multiple choice section, they will ask, if I have a circular orbit and I double my radius, how does my period change? You don't want to have to repeat all this calculation every single time. It's good to know. Yeah, it's good to know that you have this factor here. Also, I've seen in the past that they'll ask you to actually derive this. So you do need to know how to go all the way from here, all the way through this, and all the way through here. You need to know how to do that. Essentially, it's just circular motion, but gravity is your force, right? That's really all it is. Okay. So that is the mathematical representation of Kepler's third law. Now, if you want to do this for an elliptical orbit, it's totally different. You wouldn't do it like this. It's really hard. Don't worry about it. Okay, this is for circular orbits, but that's good enough. Let's look at Kepler's second law. Second law says that you sweep out equal areas in equal time. Basically means you speed up when you're close and you get slower when you're far away. When you're looking at this part of the book and if you're trying to understand what it's saying, again, the important thing to understand about an actual elliptical orbit is you have two parts. You actually have a tangential velocity and a radial velocity, right? Because when you have an elliptical orbit, sometimes you're moving away, sometimes you're coming closer. But you can split it up. How much of your velocity is pushing you away? How much of your velocity is actually turning you? That's how you want to break up the components. The turning component is the only component that contributes to your angular momentum because it's r cross p. In other words, if I took a rocket and I shot it straight from the surface of the Earth and I shot it straight up without having it ever go in a circle at all, it would have no angular momentum. It would just be straight away. So instead, most of our rockets, we tilt them as they go, and then we can just get them into orbit. Okay, so that's really where this sine beta comes from. So according to the law, it's sweeping out equal areas in equal time, so they calculate what the area is. You'll see that the way they do the area, they approximate the motion as a triangle. A lot of times this happens in calculus. What we do is we take an approximation and we take the limit as it gets smaller and smaller and smaller so that we make it a better approximation. So as this delta t gets down to 0, to a really small increment, you can essentially approximate it as a triangle. And mathematically it ends up working out to be the same. The point here is that if you look at the change in area and you look at the change in area over a change in time, it is only dependent on the angular momentum. And it's constant. It's constant. So no matter which radius you are at or how fast you're going, that is your angular momentum. Now I dug up this graduate class I took called Orbital Mechanics. I think it was Advanced Orbital Mechanics. I had to... So in astronomy, we have this thing called the n-body problem. Have you guys heard of the n-body problem? When you have two bodies in space, you do all the math, is a closed form solution, which means that you can predict for all time how they're going to move. They will move as ellipse. They'll actually move, I think, as circles. No, depending on where they start, I guess. They'll move as ellipses, and they will always go in ellipses. If you throw a third body in there, the three-body problem and beyond, there's no closed form solution. In other words, you cannot, with an equation, describe where all three bodies are going to be at all times. Because you have this pulling on this and that, and this is pulling on those two, and this is pulling on those two. So what you do is you do it numerically. You use a program like MATLAB or Python or something like that, and you calculate it out. And so this was one of my homework assignments. We got 3 masses with initial conditions, and you're supposed to calculate and predict their trajectory. These are all in dimensionless units. Okay, there's no meters, no kilometers, whatever. It starts here. This object starts here, this object starts here, this object starts here. And by their mutual attraction and gravity, they come together, but what happens? They go past each other, right? They go past each other. The closer they get to one object, the more they speed up, and then they sling away from each other.
Communication.
But I want you to look at the green line. What does the green line show? Just straight up. Just straight up. So remember what I was saying about angular momentum and that's conservation? This is a demonstration of that conservation of angular momentum. It doesn't move around. It's all its motion, whether it's slinging far out or coming close, doesn't matter. It doesn't matter. Let's see. Yeah. The angular momentum in a certain direction is just... I can't remember what the spikes are. Oh yeah, spikes are due to singularities as the masses get really close to each other. So that's really kind of a breakdown in the math when you calculate it. Like when they're right on top of each other, you're divided by 0 or something like that. Energies. Oh yeah. So this is kind of, it's hard to see, but I think I tried to plot it out from like a top view. So the idea is they're like moving in a certain direction and they're all spinning around each other, but it's
Did the masses have any initial velocities, or were they just stationary?
They do. They have initial velocity.
Were they all
You know,
going
I don't remember.
'Cause, like, on
I
the
was
first
trying to
one,
find.
It looks like,
I was trying to find the original homework questions, but I don't think I have them. Yeah, I don't have them, so I don't remember. Some of this other stuff, I have to look at what the questions were asking, but I don't remember what was asked. Something about orbiting Europa over 9 days. Using different methods for calculating where it's at, and then determining the difference between the models, the different models, something like that. But I think this is pretty interesting and just demonstrative of it, because it looks like I may have been doing some like crazy witchcraft on this. It's not. All I'm doing is in the program, I'm just using Newton's law of gravity. But you do it, where the math gets complicated is you do it with vectors, because you have to do it in 3 dimensions now, and you do time steps. You say like, okay, you do 1/1,000,000th of a second, this is the acceleration, this is how the velocity changes, this is where it's at, and then the next time step you change